Welcome to Civil Engineering Edge, where we explore the world's greatest structural marvels. Today, we uncover a legend, the Godzilla Bridge, a colossal triumph of human ingenuity and design. It's not just a bridge. It's an engineering revolution powered by the ultimate box girder, a structure so strong, smart, and futuristic that it redefines what's possible in bridge construction. From its daring conception to cutting-edge technology, this is a story of courage, precision, and creativity at scale. So, buckle up as we dive deep into the making of this modern-day mega masterpiece, the Godzilla Bridge. What if I told you that one of the most incredible bridges ever built isn't just a crossing, but a masterpiece of hidden strength? Welcome to the Godzilla Bridge, a structure so massive and so advanced that it has redefined what modern civil engineering can achieve. Beneath its graceful silhouette lies the ultimate box girder, a marvel of design and technology that quietly bears colossal loads while resisting the fiercest forces of nature. Today, we'll journey through the bridge's extraordinary conception, its groundbreaking design, and the transformational impact it has made. This is not just about concrete and steel, it's about human vision, precision, and the relentless pursuit of engineering perfection. Get ready to uncover the secrets of the Godzilla Bridge, where science meets art and imagination meets endurance. Engineering the impossible, the Godzilla Bridge's genesis. Every era has its engineering icon, a structure that pushes beyond limits and redefines what is possible. The Godzilla Bridge earned its monstrous nickname for a reason. Stretching across one of the widest and most geologically complex river valleys in the region, the project's sheer scale, strength, and ambition evoked comparisons to the legendary creature itself. The site conditions were brutal. Deep alluvial foundations, high-velocity winds, and frequent seismic tremors. Yet, the challenge only fueled the engineers' creativity. The bridge needed to span extraordinary distances without intermediate supports, meaning conventional beam systems were out of the question. That's when the idea of the ultimate box girder system emerged, a hollow, rigid, aerodynamically stable structure capable of distributing loads evenly and resisting both bending and torsion. In essence, the box girder became the bridge's invisible skeleton, a geometric marvel combining strength, stiffness, and efficiency. Its closed-cell design gave it immense torsional resistance, critical for stability under asymmetric traffic loads and side winds. Advanced finite element analysis via models simulated every load scenario, from earthquake shocks to differential temperature gradients, ensuring performance under every conceivable stress. High-performance M70 grade concrete was chosen for its durability, paired with post-tension tendons running longitudinally to provide internal compression, preventing tensile cracking. Each girder was prefabricated in specialized casting yards using match cast technology to ensure perfect alignment during assembly. Every construction phase was monumental. Cranes capable of lifting over 800 tons hoisted the massive segments, aligning them within millimeters. The bridge's aerodynamic profile was refined through wind tunnel testing, ensuring it could endure cyclonic gusts without oscillation. The result, a structure that wasn't just strong, it was intelligent. Sensors embedded within the girders monitor stress, strain, and deflection in real time, creating a living, breathing piece of infrastructure. The Godzilla Bridge wasn't just engineered, it was evolved, a testament to humanity's power to turn impossible dreams into concrete reality. From concept to groundbreaking, the visionary minds behind the marvel, every extraordinary bridge begins as a sketch, a daring idea born in the imagination of those who refuse to accept limitations. The Godzilla Bridge started as such a vision, proposed by a consortium of visionary engineers, architects, and planners determined to connect to economic powerhouses separated by an unforgiving river gorge. The early conceptual stage was a battlefield of ideas. Teams debated between cable-stayed and suspension systems before ultimately converging on a continuous box girder design, a solution that balanced strength, durability, and constructability. Using parametric modeling software, they optimized the deck's curvature and girder thickness to achieve the best performance-to-weight ratio. To refine the design, engineers conducted months of wind tunnel simulations and dynamic load testing using scaled models. The Bridge's aerodynamic profile was sculpted to minimize vortex shedding, a phenomenon that can induce dangerous vibrations. Meanwhile, computational fluid dynamics (CFD) simulations helped predict how crosswinds and temperature changes would affect long-term stability. Before breaking ground, the team confronted enormous logistical and environmental challenges. The riverbanks were remote and uneven, requiring the creation of temporary access roads, batching plants, and launching yards. Transporting 100-ton precast segments demanded custom-built trailers and synchronized hydraulic systems. The project embraced digital transformation like never before. Engineers developed a digital twin of the bridge, a real-time virtual model that mirrored every construction activity, tracked progress, and detected potential alignment issues before they occurred. Drones and LiDAR scans verified structural geometry daily, while AI algorithms optimized the sequence of segment launching to reduce cantilever stresses. Finally, after years of planning, the first segment was launched using a state-of-the-art incremental launching system (ILS). As the massive girder slid gracefully into position, the world witnessed the union of art, technology, and precision. The Godzilla Bridge became not just an engineering project, but a symbol of international collaboration, where hundreds of engineers, designers, and workers came together to create something that would stand tall for a century or more. The economic and social impact, more than concrete and steel. When the Godzilla Bridge finally opened to the public, it didn't just change the skyline, it changed lives. What once took hours of treacherous travel now takes minutes, and what was once a geographical barrier has become a seamless connection of people, trade, and culture. Economically, the bridge acted as a growth accelerator. It opened up a major logistics corridor that reduced freight transport time by nearly 40%, cutting costs for industries and enhancing trade efficiency. The increased connectivity attracted manufacturing hubs, warehouses, and smart logistics parks, transforming nearby towns into thriving economic centers. Within just a few years, regional GDP growth surged by double digits. Socially, the bridge became a symbol of unity and progress. Improved access to healthcare and education transformed rural communities, while new residential and commercial zones emerged around the approach roads. Tourism boomed. Visitors came not only for its breathtaking views, to marvel at an engineering wonder dubbed the beast that binds. But the Godzilla Bridge's influence wasn't only about development, it was also about sustainability. From day one, the project adopted green construction principles, recycled aggregates, low-carbon cement, energy-efficient batching plants, and solar-powered lighting systems along the deck. Stormwater collection channels along the box girders direct runoff into nearby wetlands, recharging the water table instead of polluting the river. The bridge also features real-time structural health monitoring systems (SHM) with embedded fiber optic sensors, helping engineers track deflections, vibrations, and temperature changes, ensuring long-term safety with minimal maintenance. For the communities that depend on it, the Godzilla Bridge stands as a living testament to engineering serving humanity. It represents connection, opportunity, and resilience. The project didn't just bridge a river, it bridged the gap between isolation and innovation. The Godzilla effect has since become a term in infrastructure economics, describing how visionary engineering can ignite regional transformation, proving once again that when engineers dream boldly, the world moves forward. To the unsung hero, anatomy of the box girder. What is a box girder? demystifying the structural genius. At first glance, a bridge deck looks like a flat slab of concrete, strong, simple, and solid. But hidden beneath that surface lies one of the most brilliant structural inventions in modern civil engineering, the box girder. Imagine a hollow rectangular or trapezoidal tube. That's the essence of a box girder. It may look unassuming, but its geometric configuration makes it an engineering masterpiece. The box shape isn't just aesthetic. It's a deliberate design that maximizes bending and torsional resistance while minimizing material usage. In simple terms, a box girder acts like a closed container that can withstand loads from every direction. When vehicles pass over the bridge deck, the girder carries both bending moments caused by vertical loads and torsional stresses caused by uneven or lateral forces. The closed shape allows these forces to be distributed evenly across the structure, reducing deformation and maintaining stability even under heavy or unbalanced loading. Unlike traditional eye girders, which can twist or buckle under asymmetric loads, the box girder's closed geometry provides immense rigidity. Its internal webs and flanges form a continuous loop, preventing warping and ensuring uniform stress flow. The beauty of this system is its versatility. It can be made from reinforced concrete, press-stressed concrete, or steel, depending on the project span and load requirements. In long-span bridges like the Godzilla Bridge, press-stressed concrete box girders are ideal because they combine the compressive strength of concrete with the tensile power of steel tendons. In visual terms, think of it as a sealed vault of strength, light, hollow, yet unbreakable. Engineers often call it the spine of the bridge, invisible to the naked eye, yet the most crucial component of the structure's survival. Through clever geometry and material science, the box girder has become the unsung hero of modern bridge engineering, quietly carrying the world's heaviest burdens, literally. Beyond the basics, inside the complexities of stress and material science, the true brilliance of the Godzilla Bridge's box girder lies not just in its shape, but in what happens inside that hollow form. Every inch of its interior is a carefully calculated battlefield of forces, bending, shear, compression, and tension, all working together in perfect equilibrium. Inside a box girder, the top flange or deck slab resists compressive forces, while the bottom flange bears tensile stresses when vehicles pass over it. The vertical webs transfer shear forces between them, creating a self-contained load path. This interaction forms what engineers call a torsionally stiff cell, capable of withstanding complex dynamic loading without distortion. But it's not just about shape, it's about material synergy. The concrete used in the Godzilla Bridge's girders is not ordinary. It's a high-performance, low-permeability mix designed to resist cracking, chloride ingress, and fatigue. Reinforced with microsilica, fly ash, and superplasticizers, it achieves extraordinary strength and durability. Inside the concrete shell lies a web of post-tension steel tendons, carefully threaded through ducts and tensioned after casting. These tendons introduce precompression, counteracting the tensile stresses that occur under service loads, keeping the structure always in compression, the secret to crack-free durability. Even temperature gradients, creep, and shrinkage were accounted for in design simulations. Engineers used finite element modeling FEM to map stress concentrations, identify potential weak zones, and optimize web thickness and flange depth. Maintenance was another major innovation. Access ducts and inspection walkways are integrated inside the girders, allowing engineers to monitor and maintain the bridge from within, like the bloodstream of a living organism being checked through its arteries. Each girder, though hollow, behaves as a living entity, reacting dynamically to traffic, temperature, and time. It's this blend of geometry, material science, and human ingenuity that makes the box girder more than a structural component. It's the beating heart of the bridge. The ultimate factor. What makes this box girder revolutionary? So what makes the Godzilla Bridge's box girder the ultimate among its kind? The answer lies in the convergence of advanced design, smart materials, and next-generation technology, making it stronger, lighter, smarter, and more sustainable than any conventional system. First, the geometry itself was reimagined. Instead of a simple rectangular profile, engineers developed a multi-cell trapezoidal girder, each cell acting like a separate structural chamber, enhancing torsional stiffness and redundancy. This configuration ensures that even if one segment experiences extreme loading or local damage, the neighboring cells share the stress and maintain stability. Second, the materials represent the cutting edge of structural innovation. The concrete mix incorporates nanosilica and basalt fibers, significantly increasing tensile strain capacity and reducing microcracking. This makes the box girder exceptionally resistant to fatigue and corrosion, extending its lifespan well beyond 120 years. Third, the box girder integrates embedded fiber optic sensors and IoT-based structural health monitoring systems (SHM). These smart sensors continuously track strain, temperature, vibration, and load response, feeding data in real time to control centers. Engineers can monitor performance remotely, predict maintenance schedules, and even identify stress anomalies before they escalate, ushering in a new era of predictive maintenance. The construction method is equally revolutionary. Using balanced cantilever and segmental launching techniques, each segment was assembled with robotic precision. Precast sections were joined using epoxy adhesives and post-tensioning cables, forming a seamless monolithic structure without cold joints. The aerodynamic profile, refined through CFD simulations, minimizes wind-induced vibrations and ensures laminar airflow, preventing oscillation even under typhoon-level winds. In short, this isn't just a box girder, it's a fusion of science, technology, and sustainability. The Godzilla Bridge S girder stands as the ultimate expression of what happens when humanity combines creativity with computation. It's silent yet powerful, elegant yet indestructible, a modern titan hidden within concrete and steel, defining the future of bridge engineering for generations to come. Building the Leviathan, construction's grand scale, logistics on steroids, the orchestration of materials, machinery, and manpower, constructing the Godzilla Bridge wasn't just an engineering challenge, it was a logistical symphony of epic proportions. Every single element, from raw materials to manpower coordination, was scaled to a level rarely witnessed in civil engineering history. The site stretched across several kilometers of rough, uneven terrain, a place where even reaching the foundation zones was a challenge. Before a single girder could be placed, a network of temporary access roads, material stock yards, and river crossing conveyors had to be built. Over 1.2 million tons of concrete, 150,000 tons of steel, and hundreds of precast girder segments were transported and assembled, all synchronized down to the minute. At peak activity, the site operated 24/7 under floodlights, with over 4,000 engineers, technicians, and workers collaborating simultaneously. Massive gantry cranes and hydraulic launching girders, capable of lifting 800-ton segments, dominated the skyline like mechanical beasts. To ensure steady supply, the project team built on-site batching plants producing customized high-strength concrete mixes under controlled temperature and humidity. Fleet management systems tracked every truck, every barge, and every piece of equipment through GPS-based logistics control rooms. Even the weather was an active design variable. Monsoon forecasts and wind data were integrated into daily schedules to prevent crane sway and segment misalignment. This wasn't construction, it was choreography on an industrial scale. Every bolt, every lift, every pour of concrete was executed in synchronized precision, where a single delay could ripple through thousands of interdependent operations. The Godzilla Bridge became a case study in megaproject coordination, demonstrating how digital planning, human discipline, and mechanical power could merge to bring a seemingly impossible structure to life. As one site engineer famously said, it wasn't just a bridge we were building. It was a city in motion, suspended above the river, precision and peril, the accuracy and dangers of building giants. Building something as immense as the Godzilla Bridge demanded more than brute strength. It required precision to the millimeter and courage to face peril at every turn. Each operation, from foundation to superstructure, carried both technical and physical risks that tested the limits of human and machine endurance. The alignment of box girder segments had to be exact within plus or minus 3 millimeters, a margin finer than the width of a pencil lead. To achieve this, total stations, laser scanning systems, and gyroscopic alignment devices were deployed continuously. Every time a 100-ton segment was lifted and positioned, engineers cross-verified its coordinates in real time using GPS-integrated survey control. The environment added to the challenge. Gale force winds over the river gorge threatened crane stability. Workers often operated hundreds of feet above the water, secured only by harnesses, performing tasks that demanded both composure and technical mastery. Seismic tremors, though minor, forced several temporary halts during deck launching operations. The cantilever construction method used here, where segments extend from opposite piers and meet mid-span, was one of the riskiest phases. Engineers relied on finite element simulations to predict deflection and counterweight balance during each launch. Even a minor miscalculation could have catastrophic consequences. Safety, therefore, became the cornerstone of progress. Over 3 million man-hours were logged without a single fatality, a record achieved through rigorous training, strict PPE enforcement, and the use of automated lifting systems to minimize human exposure. Drones provided aerial surveillance, identifying potential hazards in real time, while AI-driven safety dashboards flagged temperature, wind, and load anomalies. In the end, it wasn't just engineering precision that made this bridge possible. It was the discipline, bravery, and adaptability of every person involved. Amid wind, height, and danger, the builders of the Godzilla Bridge achieved the impossible with unwavering focus, turning peril into progress, one segment at a time. Behind the scenes, the human story of triumph and tenacity. Beyond the blueprints and machinery lies the true soul of the Godzilla Bridge, the people who built it. Behind the roaring cranes and concrete mixers were men and women whose sweat, skill, and spirit transformed vision into reality. Daily life on the construction site was a story of endurance. Workers began their shifts before sunrise, donning safety gear and attending toolbox meetings that outlined every hour's critical operations. Engineers huddled around digital screens in mobile command units, analyzing real-time sensor data, weather updates, and lifting sequences. The rhythm of machines became the heartbeat of the project. Concrete pumps hissed, steel cables sang under tension, and generators roared in unison. Each milestone was celebrated like a festival. When the first box girder segment was successfully launched, the entire crew erupted in applause, a moment that symbolized not just technical victory, but collective pride. Interviews with site supervisors revealed the emotional depth of their mission. We weren't just constructing concrete, we were constructing history. The human challenges were immense. Long shifts, intense weather, and remote locations tested morale. To keep spirits high, the project management set up temporary townships, complete with food courts, recreation zones, and medical facilities. Workers from multiple countries shared meals, cultures, and stories, creating a living mosaic of unity through engineering. Filmmakers and documentarians captured these unseen moments, the grit-stained faces of welders, the quiet concentration of surveyors, and the laughter of workers resting under floodlit skies. Every frame told a story of collaboration, sacrifice, and triumph. In the end, the Godzilla Bridge became more than an engineering structure. It became a symbol of humanity's collective will. The real heroes weren't just the machines or the technology. They were the countless individuals who believed that every bolt and beam was part of something eternal. Their story reminds us that the greatest bridges aren't just made of concrete and steel. They rebuilt from dedication, resilience, and hope. Facing the elements, durability, and future-proofing for the YouTube video Godzilla Bridge, the ultimate box girder unveiled target audience. Civil engineering students and professionals, the ultimate test, strength against nature when you design a bridge of this scale. One that stretches across deep waters and connects continents. The biggest question isn't can we build it, but can it last? The Godzilla Bridge faces some of the most unforgiving natural challenges imaginable. From hurricane force winds and salt-laden air to seismic tremors and torrential rains, this structure was built not just to survive, but to endure. Engineers began with extensive wind tunnel testing. Scaled models of the bridge were subjected to simulated typhoons, ensuring the aerodynamic shape of the deck and the box girder could cut through gusts exceeding 250 kilometers per hour without fluttering or vibration instability. The box girder itself, a hollow, rectangular steel-concrete hybrid, acts like a closed tube, providing both torsional stiffness and aerodynamic stability. For seismic resistance, the foundation sits on giant friction pendulum bearings capable of moving during an earthquake, dissipating energy instead of transmitting it to the deck. The Godzilla Bridge can withstand quakes measuring over 8.0 on the Richter scale. Even the concrete mix was engineered to fight time and nature. Using nanosilica additives, corrosion inhibitors, and fly ash, the high-performance concrete minimizes chloride penetration, essential for structures over marine environments. The outer steel surfaces are coated with multi-layer anti-corrosive epoxy systems and cathodic protection to prevent rusting. Finally, a drainage and dehumidification network runs through the internal chambers of the box girder, preventing water stagnation and corrosion. In short, the bridge is more than an architectural marvel. It's a fortress of engineering foresight, ready to face decades, even centuries of environmental assault. Smart bridge technology, intelligence in steel and concrete. What makes the Godzilla Bridge stand apart isn't just its strength, it's its intelligence. Engineers designed it to be self-aware, capable of detecting issues before they become problems. This is where the world of civil engineering meets the Internet of Things IoT. Embedded within the deck and girders are over 2,000 smart sensors, strain gauges, accelerometers, temperature probes, and fiber optic lines that monitor everything from internal stresses to vibration frequencies. These sensors transmit real-time data to a centralized control hub where engineers can visualize the bridge's health on dynamic dashboards. If there's even a minute crack formation, differential movement, or abnormal vibration, the system flags it instantly. Predictive maintenance algorithms analyze this data, estimating where and predicting future maintenance requirements. This allows engineers to intervene precisely when needed, minimizing downtime and maximizing safety. Drones equipped with high-definition cameras and thermal imaging regularly scan the bridge's exterior, identifying surface irregularities invisible to the naked eye. The lighting and navigation systems are solar-powered and connected to an energy management network that adapts brightness according to traffic and visibility. Even the dehumidification system inside the box girders is automated, ensuring the interior remains moisture-free. Essentially, the Godzilla Bridge is alive. A digital twin of the structure exists in a cloud-based system, continuously comparing expected performance with real-time data. This living bridge concept represents the future of civil infrastructure, where engineering excellence meets artificial intelligence. The result, a bridge that doesn't just exist in time, but adapts to it. Innovations for tomorrow. Legacy of the Godzilla Bridge. Every great structure teaches future engineers how to build smarter, stronger, and more sustainably, and the Godzilla Bridge is no exception. The innovations born here are already influencing next-generation projects worldwide. The Bridge S-Box girder design introduced a new hybrid composite, ultra-high-performance concrete UHPC reinforced with carbon fiber polymers, making it 30% lighter, yet twice as strong as traditional designs. This advancement is being adopted in long-span bridges and elevated metro viaducts globally. Sustainability was another cornerstone. Over 40% of materials were recycled or locally sourced, drastically reducing carbon emissions during construction. Lessons learned in efficient logistics and modular precasting have redefined project management strategies for future megastructures. Perhaps most transformative is the digital integration model, where civil engineering merges with AI, machine learning, and cloud analytics. The Bridge-S digital twin concept is now serving as a prototype for smart cities and intelligent infrastructure planning. Educationally, the Godzilla Bridge has become a case study in universities and engineering institutes across the world. It is inspiring a new generation of engineers to think beyond blueprints, to imagine bridges as living systems that sense, respond, and evolve. From its foundation to its sensors, the Godzilla Bridge represents a promise that human ingenuity, when paired with technology and vision, can conquer nature's challenges. Its story isn't just about steel and concrete, but about redefining what's possible in the art and science of building for the future. A monument to human ingenuity beyond the numbers, aesthetic marvel, and symbolic importance. When we talk about the Godzilla Bridge, it's easy to get lost in the technical grandeur, the tonnage of steel, the span length, the load-bearing capacities. But beyond the equations and blueprints lies something even more profound: art in motion. The bridge is not just an engineering triumph. It's a symbol of human imagination and creativity cast in steel and concrete. From a distance, the bridge's sweeping arcs appear like the spine of a colossal creature, a poetic nod to the Godzilla name. By day, it gleams with the brilliance of precision. By night, it transforms into a luminous ribbon of light, its lead facade reflecting off the water below, creating a breathtaking visual symphony. The bridge's aerodynamic profile, inspired by natural forms like whale fins and bird wings, harmonizes function with beauty, proving that engineering and aesthetics can coexist in perfect balance. But the symbolism runs deeper. The Godzilla Bridge stands as a global emblem of resilience and unity, connecting not only to land masses, but also cultures, economies, and generations. It represents humanity's determination to conquer impossible challenges, to reach beyond limits, and to create something timeless. For the people it serves, the bridge is more than infrastructure, it's identity. It has redefined skylines, fueled tourism, and become a visual landmark recognized worldwide, a beacon of progress standing tall against nature's might. In every curve and cable, the bridge tells a story of courage, collaboration, and creativity. The legacy continues, inspiring new generations. The Godzilla Bridge is more than a structure, it's a classroom suspended in the sky. For engineering students, it's a living textbook of design excellence. For professionals, it's a benchmark of innovation. For dreamers, it's proof that no vision is too big. Across universities worldwide, the bridge is studied as a pinnacle example of modern design philosophy, combining sustainability, digital intelligence, and structural performance. The lessons from its construction are influencing new paradigms in civil infrastructure, where projects are not merely built, but engineered for life. Young engineers are particularly inspired by the story of the project's creators. The multidisciplinary teams of designers, data scientists, environmental experts, and workers who together made the impossible possible. The Godzilla Bridge has reignited a passion for large-scale public works, reminding the world that civil engineering remains one of the purest forms of applied creativity. Even in the professional world, the bridge has sparked innovation. The concept of smart girders and digital twins used here has become a model for future megaprojects, encouraging new collaborations between technology firms and civil engineers. Workshops, documentaries, and international symposiums dedicated to the Godzilla Bridge continue to inspire those who dare to dream bigger. Ultimately, its legacy isn't just the structure itself, it's the mindset it leaves behind. That no challenge is insurmountable when vision meets determination. The Godzilla Bridge isn't the end of an era, it's the beginning of a new one. Experience the marvel, a call to action. If you ever get the chance to stand before the Godzilla Bridge, take a moment, not just to look, but to feel. As you gaze across its vast expanse, you'll sense the quiet hum of power beneath its deck, the pulse of millions of hours of human labor, and the spirit of innovation that brought it to life. Visitors describe walking across it as a transcendent experience, the rhythmic thrum of vehicles echoing through the hollow box girders, the panoramic view of sky and sea, and the subtle vibration of engineered perfection beneath your feet. Observation decks and visitor centers along the approach offer immersive experiences, including AR visualizations that reveal the bridge's inner structure and the forces that make it stand tall. For students and professionals, this is more than sightseeing, it's inspiration made tangible. You're not just witnessing a feat of construction. You're standing atop generations of human progress. Every cable, bolt, and beam is a reminder that imagination has no ceiling when guided by science. So here's the challenge. Let the Godzilla Bridge awaken your curiosity. Let it push you to design smarter, build stronger, and think bolder. Whether you're sketching your first truss design or managing billion-dollar infrastructure, remember that even the greatest monuments begin with a single idea, one courageous thought that defies the impossible. Because in the end, the Godzilla Bridge isn't just a bridge, it's a mirror reflecting what humanity can achieve when innovation, purpose, and passion unite. The Godzilla Bridge stands as proof that when innovation meets determination, humanity can build beyond imagination. From its powerful box girder core to its living smart systems, it's more than infrastructure, it's a symbol of our collective potential. For every student, engineer, and dreamer watching, let this bridge remind you that boundaries exist only to be pushed. Don't just admire engineering, become part of it. If you enjoyed this journey through the Godzilla Bridge, subscribe to Civil Engineering Edge for more deep dives into the marvels that shape our world. Until next time, keep building the future.